Hey everyone, welcome to This Explainer. Today, we're diving straight into the critical, yet honestly often misunderstood, role of ultraviolet light in keeping dialysis water safe. It's a totally fascinating piece of medical engineering from our source material that is absolutely essential for patient safety. So let's unpack exactly how it works.
Right off the bat, there's a really common misconception we need to address. You might be wondering, how does UV light physically remove bacteria from dialysis water? When we think of water treatment, you probably picture some sort of microscopic net, or maybe a high-tech laser beam that just zaps bugs on contact to completely clear them right out of the pipes.
Well, here's the surprising reality. It doesn't. It literally doesn't. UV light isn't a bouncer physically throwing microbes out the door of our water system. Instead, it actually acts as a highly specialized, completely invisible saboteur.
Section 1. The role of UV, the microscopic assassin.
And this brilliantly illustrates the core difference we really need to grasp here. To understand its true purpose, the source material defines UV as a specific form of electromagnetic radiation. Think about regular filtration that physically removes particles in organisms, trapping them so they literally cannot pass through. UV exposure, on the other hand, leaves the organisms right there in the water, but it inactivates them. Filtration removes the physical threat, whereas UV neutralizes the biological threat from the inside out.
Section 2, How UV Destroys DNA, the Mechanism of Action.
Okay, let's dive into this and look at the exact microscopic attack this radiation launches on bacteria, viruses, and protozoa. It's basically a three-step assassination process. Step 1, the UV light penetrates the cell walls, completely bypassing their outer defenses. Step 2, it directly damages their DNA. And step 3, this damaged DNA absolutely prevents replication. The light destroys the cell's fundamental ability to reproduce. And, if a bacteria cannot replicate, it cannot establish a colony, and it can't cause an infection. Basically, game over.
The exact terminology used in the source data here is really fascinating, and it's the word inactivate. It literally means to render a microorganism completely unable to replicate or cause harm without actually physically filtering it out of the water. So remember, UV does not filter, it inactivates. The organism is technically still floating right there, but it's been rendered entirely harmless.
Section 3. Inside the UV chamber, the physical weapon. So we know the microscopic damage being done, right? But what does the actual physical machinery look like in a working dialysis water system? Well, first you've got a clear quartz sleeve that houses the UV lamp. And quartz is used because it allows specific UV wavelengths to pass through completely unblocked, unlike standard glass. Second, the water flows directly into an exposure chamber. Third, as that water is forced precisely around the quartz sleeve, it gets blasted with intense radiation. Ultimately, this really intense, calculated exposure successfully reduces the microbial load.
But here is the catch. For this chamber to actually work as intended, the environment has to be perfect. It absolutely demands clear water and proper flow conditions. I mean, think about it. If the water's murky, those physical particles cast microscopic shadows, basically giving bacteria a physical place to hide from the light. And if the water flows too quickly, the bacteria might just zoom right past the lamp without absorbing a lethal dose. So environmental clarity and mechanical timing are literally everything here.
Section 4. Limitations of UV treatment. Knowing the blind spots.
Now, while UV is a powerful microscopic assassin, the source material notes it is by no means a magic bullet. Let's rapidly walk through its blind spots. 1. It doesn't remove physical particles. 2. It doesn't destroy endotoxins. Those are the toxic pieces of cell walls left behind when the bacteria die. 3. It only inactivates microorganisms present at the exact time of exposure. And 4. It provides absolutely zero residual disinfecting effect. But look, these aren't failures. They're the exact reasons why UV requires pre-filtered water and acts as a specialized player on a much larger medical team.
I really want to highlight that last limitation because it's absolutely crucial to understand. There is no residual disinfecting effect after the water leaves the chamber. This is not like adding chlorine to municipal water where it travels through pipes killing bugs miles down the road. UV is purely a point-in-time treatment. The very moment water flows out of that glowing chamber and into the dark pipes of the clinic, it is completely on its own. If new bacteria are somehow introduced downstream, the earlier UV treatment offers zero protection against them.
Section 5, The Final Takeaways, Building a Complete System.
So, the crucial point is, how does this highly specialized tool actually fit into the broader objective of keeping patients safe? Let's quickly recap the absolute essential rules. 1. UV inactivates via DNA damage. Again, it is not a filter. 2. It absolutely requires clear, particle-free water to eliminate those shadows where microbes can hide. 3. Proper flow is essential to ensure adequate exposure. And 4. It cannot remove endotoxins. Honestly, locking down these 4 fundamental concepts gives you a massive advantage in understanding how water purification logic actually works.
Which leads us to the overarching takeaway from all of this. UV is just one single component of the overall dialysis water treatment system. It's a single, vital tool working alongside carbon tanks, reverse osmosis membranes, and ultrafilters in this highly orchestrated sequence. It plays its specific role flawlessly, for sure, but it relies entirely on the rest of the system to cover its blind spots.
And that leaves us with a pretty fascinating puzzle. Because if the microbes are still in the water, just inactivated, well, what removes the rest of the physical threats? What handles the endotoxins or strips out the dangerous chemical contaminants? UV does its incredibly precise job of stopping biological replication, but man, there is so much heavy lifting happening behind the scenes. It really makes you wonder just how complex the rest of that dialysis water treatment machinery truly is, doesn't it? Thanks for joining me for this explainer, and keep asking great questions.